So we're in section 2.2. So we're going to talk about polynomial functions. Yes, the other day we talked about quadratic functions, where we have our highest power is the second power. So we're going to talk about polynomials that have higher powers. And just a quick reminder, we're talking about a function that looks like a to the n, x to the n plus some other number, and minus 1, x to the n minus 1, dot, dot, dot. We're going to keep adding terms. So we said our polynomial function looks something like this. So we have just a bunch of powers of x to the fifth, x to the fourth, x to the third, all the way down to some constant. So this is what we're talking about when we're talking about a polynomial function. The first thing that we're going to talk about is graphs. What graphs of polynomial functions look like? We already know what a graph of a quadratic function looks like. A graph of a quadratic function is going to be a parabola. It's either going to open up or open down. Well, we can figure out a couple of things of graphs of polynomial functions. The graphs are, we're going to say that the polynomials are continuous. So that means our graphs are going to be, are not going to have any breaks or gaps. And graphs of polynomial functions are smooth. So that means we don't have any sharp corners. So just a couple of sketches. If I have a graph that looks like this, so this is just an example of a graph. This would not be a polynomial. So we have a break in the graph. We have some kind of jump in the graph. So this would not be a polynomial. And something like the absolute value graph, where we have a V shape, would not be a polynomial. We never have a sharp corner with a polynomial. So our graphs are always going to be smooth and nice. So the first thing that we're going to look at today is how the graphs of just a couple of really simple polynomials. We're just going to look at one term. We're going to say f of x. We're going to look at the graphs of f of x equals x to some exponent, x to the n. Where n is bigger than 2. We just want to know what these graphs look like. So these graphs, when we have something like this, we're going to call these power functions, because it's just x to some power. So let me grab a picture. I have a picture of some power function here. We're going to talk about them a little bit. So there are the graphs of some power functions. In black is f of x equals x squared, a nice parabola. In red we have x to the fourth. We're looking at just even power functions. So in red we have x to the fourth. In blue we have x to the sixth. And in green we have x to the eighth. So these power functions, they kind of flatten out as the power gets higher, but they all look more or less like parabolas. So for all of these, n is even. And what we're looking at here is that our graphs flatten out as the powers get higher. So let's look. So any power function where the highest power is even is going to have something in common with these graphs. So let's look at the power functions where n is odd. I'm going to go down here. We're going to go to the second page. I'll grab this. So for these power functions, n is odd. Again, they get a little more flat as the odd powers get higher. This is x to the third. In red is x to the fifth. In blue is x to the seventh. And in green is x to the ninth. So they flatten out as n gets higher. And notice with the odd functions, on one side it goes up, and on the other side it goes down. Or for the even functions, it went up on both sides. So these are our basic power functions. First one looks kind of like x squared. These all look kind of like x cubed. Power functions transform, meaning that they shift around just like parabolas. So if we were to look at you could call this an S curve. Usually you just, if you looked at this, I would say this is y equals x to the third, would be my first guess, or a cubic. So this looks like a cubic, but any of the odd power functions are going to look similar to this. So I just wanted to show you our basic power functions. The even ones, they look like x squared. The odd ones look a lot like x to the third. They flatten out as n gets bigger. So our power functions transform just like any of our other graphs. And by transform, I mean if we were looking at a graph, if we wanted to figure out what the graph of f of x equals minus x plus 2 to the fourth looks like, this minus out in front, what does that do to any graph that we're transforming? Flips it upside down. And the plus 2 is going to move it, we've got plus 2 inside the parentheses. How does that move it? To the left. It's opposite. When it's inside the parentheses, it's opposite. So this is going to be flipped. And left 2 units. So if we were to sketch a rough graph of this one, and it's just going to be really quick. It's flipped upside down and it's shifted to the left by 2. And we know that x to the fourth looks kind of like x squared but kind of flattened out. So here we're at negative 2, so my graph is going to look like, roughly, like this. So kind of like a flattened out parabola shifted over to the left 2 and upside down. So they transform just like any other function. Let's look at another quick example. If we have f of x equals x minus 3 to the 5th plus 4. So what are we doing to this graph? So this is going to be right 3, up 4. And it's going to look something like x to the 3rd. So if we were to sketch a quick graph of this function, we would have, we're going to go to the right 3 and up 4. I'm doing a very rough sketch. My graph would go through here and it would be kind of flattened out. It would look something like that. That's a very rough sketch. So we're just shifting our graph over from going through 0, 0 to shifting it right 3 and up 4. So that's just a rough sketch. So power functions transform. They shift around just like any other functions, just like functions that we've shifted around in the past. So we have a rough idea of what power functions look like. We know they shift around, they transform just like any other function. The other thing that we're interested in is what happens to them as x gets very, 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 very big or x gets very, 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 very small. One nice thing about power functions, about polynomials, is that they behave nicely. We already said that they're smooth, they don't have gaps, they don't take sharp turns, and what they do eventually when x gets really big and really small is very predictable also. So I want to look at some other graphs. What we're trying to figure out here is, the next thing we're trying to figure out is what we call end behavior. So end behavior just means what happens eventually. So let me get another picture here, and we're going to talk about the end behavior of some of these polynomial functions. What happens eventually? So I'm just shrinking this down a little bit so we can talk about it. So here are some graphs. Here's some graphs, and our polynomial functions are all of even degree. When we talk about even degree, we mean that the highest exponent is even. So let's look at these functions. This first one in black is 2x squared plus 3x minus 4. So that's just a nice parabola. The second one in red, x squared plus 3x plus 2, is just a shifted parabola. The blue one, x to the 4th minus 3x squared plus 2x minus 1, does a little more complicated thing here. And the green one, we have a minus x to the 4th, so it's flipped upside down. Now looking at all four of these graphs, what happens as x gets really, really large on all of them? Are they changing direction? Are they coming back down? Or are they just eventually are they increasing? As I go further this way, do the graphs come back down again? No. They just keep going up and up and up, up and up and up. This one's flipped upside down. Eventually, it just keeps going down and down and down and down. If I expanded the graph, these graphs aren't ever going to come back down. So eventually, all of these graphs, and are they doing the same thing or different things on the left-hand side and the right-hand side? So if we look at the red one, on the left and the right, eventually, is it going up, going down, or is one side going up and one side going down? Both going up. Same thing for the black one. Same thing for the blue one. Eventually, they're both going up on both sides. For the green one, where it's flipped upside down, eventually, both sides are both going down. So let's look at. So these are our even powered polynomials. The highest power, highest exponent is even. So let's look at what happens with the odd powered polynomials. So here are our odd-powered polynomials, where n is odd. All right, guys, let's listen up, guys. The one in black is x cubed minus 2x squared minus x plus 1. So that's this one. So eventually on the right-hand side, it keeps going up, and eventually on the left-hand side, it keeps going down this way. The red one is 2x to the fifth. The highest power is x to the fifth. Eventually on the left, it goes down. Eventually on the right, it goes up. The blue one, I have a negative 2x to the fifth minus x squared plus x plus 5x plus 3. This one on the left, eventually it goes up, and on the right, eventually it goes down. That's one of the nice things about polynomials is they always do the same thing eventually on the left and the right. So we're going to make a table that describes what their end behavior is, what they eventually do. And we call this the leading coefficient test. This should be leading coefficient test. And by the leading coefficient, what we're talking about is the number is the number in front of the highest power of x. So we're going to say that we're going to make a table here, and we're going to say that the term with highest power of x so we're talking about our function f of x is ax to the n plus something else. But we're talking about the highest power of x here. So we're just looking at that term. We're going to make a table for the leading coefficient positive. So the leading coefficient is a. This is what we're talking about, this number a that's in front of the highest power of x. So we have one thing that happens when a is positive, and one thing that happens when a is negative. And we also have something, we're on this side of our table, we're going to have n is even and n is odd. So we're making a table of what our end behavior is. What our end behavior is. If our leading coefficient, if a is positive, so the coefficient on our highest power of x is a positive number, and our highest exponent is even, our end behavior is that our function eventually on the left goes up, and on the right it goes up. So this is our end behavior. If a is negative, so if we think of a parabola here, n is 2, so we think of x squared, y equals x squared, eventually on both sides it goes up. If a is negative, eventually our end behavior is that our function goes down on both sides. If n is odd, our function goes down on the left and up on the right if a is positive. So that's what y equals x to the third looks like. And if a is negative, we're just flipping our function over. So it goes up on the left and down on the right. So this is a chart that tells us our end behavior. What happens when x gets really big? What happens when x gets really small? So polynomials are nice because their end behavior always follows this pattern. If our highest power on x is even, and the leading coefficient is positive, it eventually goes up on both sides. If the leading coefficient is negative, it eventually goes down on both sides. If n is odd, if a is positive, it goes down on the left, up on the right. If a is negative, it goes up on the left, down on the right. And this is for any polynomial. So questions on our test. We'll look at a couple of examples in just a second. All right, so we want to describe, one way that you'll be asked this question is to describe the right and left hand behavior. So for the first one, we're going to have f of x equals minus x to the fourth plus 7x to the third minus 9. So what this is asking us is, what does this eventually do? So what's our highest power here? Our highest power is x to the fourth. And what's our leading coefficient? Leading coefficient is -1. So this is the highest power, and the number that's in front is -1. So our leading coefficient equals 4. Leading coefficient is -1. So our end behavior is going to be down and down. Down on the left, down on the right. So this is going to look kind of like a flipped over parabola. So on the problems that ask you to describe the left hand and right hand behavior, drawing these little arrows is all you really need to do. Goes down on the left, goes down on the right. For an odd power, so if we have f of x equals, let's say 5x to the fifth plus 2x to the third minus 14x squared plus 6. So what's our highest power on x? Highest power on x is 5. So n is odd. Our highest power is odd. Our leading coefficient is 5. And 5 is positive. So our end behavior, n is odd, our leading coefficient is positive, so our end behavior is going to be down on the left, up on the right. So we're not worried about what the graph does in between. It can do all kinds of other stuff in between. All we're worried about is what happens eventually. If we go way far to the left or way far to the right, this is going to be our end behavior. No. No, so if you were given this question on a test and it said, what is the end behavior, and you drew these two arrows, that would be all you'd need to do. All right, we have one last thing to talk about. Is the zeros of polynomial functions. Now moving forward, when we're working with polynomials, it's going to be really important to remember that all of these things mean the same thing. I'm going to make a list. One, x equals a is a 0 of f. So we're talking about a function and a is a number. So x equals a is a 0 of f. That's one way of saying something about this function. X equals a is a solution . X equals a is a solution of f of x equals 0. These two things mean the same thing. X minus a is a factor of f of x. And the last statement that means the same thing, the number a, the point a0 is an x-intercept of the graph of f. So all four of those things mean the same thing, and we will use these not quite interchangeably, but we'll talk about them all to mean the same thing. So if we want to find the x-intercepts of a function, we have to find where f of x equals 0. If we know that a number is a 0 of a function, that tells us the x-intercepts. If we know that we have an x-intercept, that tells us that this number is a solution of our function. So all of those things tell us the same thing about a function. So let me do one quick example, and then we'll be done using this idea. If we want to sketch a graph. Sketch a graph of x to the third minus 2x squared. Well, first off, let's look at the end behavior, because we can figure that out. The highest power is 3. The leading coefficient is positive. So the end behavior is going to be down on the left and up on the right. So if we draw our axes, we know right away that our graph eventually is going to go down this way, and eventually it's going to go up this way. So what happens in between here that we're interested in? Well, we can figure out where it intercepts the x-axis. So if we figure out where it intercepts the x-axis, we can get a rough idea of what it does in between here. It intercepts the x-axis when f of x equals 0. So I'm going to say x cubed minus 2x squared equals 0. That's going to tell us where it crosses the x-axis. Now what can I do to solve this? How can I figure out where this equals 0? Factor out an x squared. X squared times x minus 2 equals 0. So where is it going to hit the x-axis? X equals 2 and x equals 0. So I know that it's going over on this side. It's going to go through the x-axis at x equals 2. It's going to have to touch 0, because if it went up here again, if I went this way, wouldn't it have to go through the x-axis again to eventually go down? And it doesn't go through the x-axis anywhere else. So it has to go back down here. So this is a really rough sketch of the graph, just knowing the end behavior and just knowing the intercepts. We could plot some additional points to make it more accurate. We could just plug in some values for x to get some additional points to make our graph more accurate. I could plug in x equals 1 and figure out where we are down here. I could plug in x equals negative 1 and get a point over here to get a more accurate picture of my graph. So this is one way we use the end behavior and the zeros to get a rough sketch of our graph. All right, homework.
I know everything. I'm probably in so many places.
Is that a 4 or a 9? You think I should keep it as a 4? Let me look. It is a 9. There you go. Odd.